Welcome back, ELE 112. This is section 19-2 on high-pass filters. We essentially covered pretty much everything we needed to know in section 19-1 and then some. To be able to work through high-pass filters at a much more brisk pace. So I want you to know that up front, that we should be skating through here. Here's a box representing the high-pass filter. We know that it's going to be this circuit, or it's going to be this circuit, or it's going to be that circuit, or it's going to be that circuit. The output is always taken in the downward component, and what we get is a frequency response curve that looks like kind of like the opposite of a low pass, where the stuff in green is rejected, the stuff in red passes freely. The further you get to frequency, the more that it passes. Everything we learned in the last video about dBs, decibels, continues to count. We definitely could do Bode plot with volts, like what you're looking at right here is just volts. It's a lot easier going to decibels, and it makes for the plot is a lot easier when that happens. Here's Bode plot for a high-pass circuit. Again, I'm going to bring this line down here. This is what you're used to seeing, and the frequencies can be transferred to the bottom. And this line that you're looking at, the response curve for a high-pass filter, I want you to take note that there is a red line and a blue line on top of each other. And this was the case with a low-pass filter as well. So I want you to notice that the blue line, which is right here, is a realistic line, while the pink line up here is the ideal line, which means, you know, you do an analysis on paper, you get the ideal voltages. Things are perfect. The ohms all match out. The capacitors and inductors all match out. You can theoretically draw the red line in a perfect world, but realistically it curves a little bit. It's nonlinear in that region, and but that is the shape of the curve. And the rise over run that you see here is exactly the same as a high-pass filter. This is right here and right here, 20 and minus 20 and minus 40 dBs per decade. And we certainly have a decade of frequency going on up here. 0.01 of whatever the center frequency is, and 0.1 of the center frequency is a 10-to-1 difference. A decade is what we call it. And so we get minus 20 decibels, minus 20 B per decade of decay in this curve, or in this case, rise. It depends on what you're talking about. If you're talking about the frequencies going down, we're talking about decay. If you're talking about the frequency going up, we're talking about the rise of the wave. Here's a little more detailed drawing, and it looks like the cutoff is somewhere in this region right here. And that puts you between 1 and 10,000. That might be 1, 2, 3, 4, 5. Could be 5,000, 6. Looks like the cutoff actually might be right here at 10K, actually, at 10K. So, you know, there is the 10K that shows you the curve. We don't really need the rest of the curve. We know it's going to be a straight line. And as far as looking at the flat line that's diving here, this one here that's in green, between 1,000 and 10K is a decade of 10, and you can see theoretically, we're going from 0 dBs here, 0 dBs, to minus 20 dBs here. You might have forgotten what 0 dB is. 0 dB means no gain and no loss. It means when I put 10 volts in, peak to peak, I get 10 volts out, peak to peak. Remember, these circuits cannot amplify. They can attenuate, they can drop in value, and in the real world, if you were to fire up a 10 volt peak to peak signal, you might get only 9.8 coming out of it, 9.7, 9.6. Without putting an amplifier out there, you're not going to get more than you put in. Now, important to say it again, this graph is a Bode plot, B-O-D-E. It is a frequency response curve that plots frequency versus voltage slash dB. We have converted the voltages to decibels. And you see it makes a really nice linear looking graph going up and down. And what else? What else we want to talk about? The minus 20 dBs per decade still holds on a high pass. And we are using log, semi-log graph paper. You can find that for free online. So here's an example of a high-pass filter with an inductor and a resistor, and you'll notice that the output is being taken across the inductor, which leads me to believe that if I wanted to do the same thing with a capacitor, this would get it done. Let's think about this. Let's logic it out and see if it makes any sense at all. I'm just guessing at this point. I'm hypothesizing. Since the inductor is here in this circuit down below, there's no way that I could put a capacitor there and expect it to work like a high-pass filter. There's just no way. So, to justify my thoughts, First, we'll talk about the circuit in red. This is an inductor, and at very low frequencies, 0 is pretty low. At very low frequencies, it's just a piece of wire, and the output is 0. 0. Now, as the frequency goes up, 2 pi FL kicks in, and as the frequency goes up, the resistance goes up, and it exceeds the value of the resistor. So now most of the voltage is across the inductor, and you get a high-pass filter response, okay? Something else worth saying. The equation for cutting off the cutoff is shown down here at the bottom of the page. I want you to take a peek in the green circle, make note, put it on your formula sheet, have it handy. You'll need it for homework. Okay? Typical homework problems are going to be just like the ones you saw in the low pass section. So we won't need to do too many in this section. I believe we'll be able to get away with just having the sample problems in the low pass section of the chapter. Now, this circuit right here is a capacitor, and at DC, capacitor looks like this. So let me ask you, how much voltage gets to the output if the capacitor's in the way and there's a roadblock here? How much voltage? You got it. 0. And as the frequency gets higher, this capacitor dead shorts. Here it is, dead shorting, 0 ohms. And who gets all the current, all the voltage? The resistor. And at the cutoff and beyond, we are at full voltage. Okay? Or theoretically full voltage. That concludes our high-pass filter information.